In this video, we're going to continue with antiderivatives and take it up a notch. We're going to do the antiderivative of functions that would have required the chain rule to do the derivative of. So integration by simple substitution or by u-substitution is how we're going to go about finding antiderivatives, as I just said, when the original function would have required the chain rule. So as an example, let's remind ourselves of what the chain rule is. So if your original function was, let's just use a really simple example. The original function was sine 2x instead of just sine x. We know that the derivative of sine is cosine, but there is a 2x instead of just an x inside this sign, and therefore we would have to say it's the cosine of 2x with the inner function unchanged, and then multiplied by 2, which would be the derivative of the inner function. And so the final answer would be 2 cosine 2x for the derivative. So what we're going to be dealing with today is how we're going to integrate a function that is slightly more complicated, where the original function would have required chain rule. So we will be looking at things like this. The way we're going to go about doing it, and I'll just preview it with this, is to take the inner function that we recognize here in our function, and as we try to find the antiderivative, we're going to write over here on the side that u is equal to 2x. We're going to define u to be 2x, and that way we can rewrite the integral that we're trying to do as 2 cosine u. Cosine u is like cosine x, and so it's a very simple function that we actually can do the antiderivative of using the formulas that we have in our formula booklet. So we basically turned it into one of the rules that we do know from our formula booklet. There's nothing in the formula booklet that says what the antiderivative of cosine 2x is, but there is something in the formula booklet that says what the antiderivative of cosine x is, and cosine u is the same as cosine x, just with a different letter. So now we can do the antiderivative. However, we have this 2 sitting around. So there's going to be this added step of, after we've defined what u is, to write down what du dx would be. And this is a notation that you might remember means derivative. So we actually want to write down what is the derivative of the u that we've just defined. So basically looking to take the derivative of this 2x statement. The derivative of 2x is just 2. So what we see is that this extra 2 that is sitting over here actually matches this derivative of the thing that we've defined as u. So in place of the 2, actually I'm going to go back over here and pass this dx to the other side by multiplication. We've got a 2 and a dx, right? So I forgot to carry this dx down. So in place of this 2 and this dx in the integration that we're trying to do, I can replace 2 dx with du. And so the thing I end up actually integrating is cosine u du. Once I have gotten the u and the du to match, right, I've got the period at the end of the sentence. Du matches the variable that's in the function that I'm trying to get the antiderivative of, so cos u. We would not have been able to do the antiderivative at this step because dx does not match the u variable that I'm looking at. But now I've got them to match because I did a little substitution, and now I can actually do the antiderivative of cosine u. So I put a little equal sign to show I am now actually removing the integration symbol. I'm going to do the antiderivative of cosine. Because the derivative of sine is cosine, the antiderivative of cosine is sine. Don't forget to put a plus c when you do an antiderivative. And of course, the original question wasn't in terms of u, it was in terms of x. So we want to change our u back to the thing that we defined u to be, which was 2x. So we'll put sine 2x plus c as the antiderivative of 2 cosine 2x, which we knew was going to be the answer because that's actually how we started this slide. So that is the u-substitution for antiderivatives in action. And it seems very complicated when you first do it out like this. Eventually, it's going to be so routine for you that it won't feel this complicated. So the rest of the slides are really just practice, and we're not going to do every example in this video. Oh, forgot this slide is a useful tip. You might want to pause and note for yourself. It is good practice to compute the derivative of your answer to make sure that you got it right. Make sure that you did the integration correctly. So if I go back to the slide we were just on, to check that my answer is correct, that's sine 2x, I can just do the derivative of sine 2x using chain rule, and it also lets us practice chain rule, never a bad thing. So the derivative of sine 2x is going to be cosine 2x times 2, which simplifies to 2 cosine 2x. Of course, the derivative of the c is just 0, so I don't need to show that. And indeed, this is the function that we started with inside of the integration symbol, so I got it right. So it's good practice to check. And then, like I said, here's a bunch of examples, and we are not going to do them all. We will do a few of them, just so you can start getting into the routine of this thing. So let's start with example A. It looks really complicated. In fact, it's chosen numbers really nicely to make it work out for you. So what I recommended doing for u-substitution, you see a complicated function, you're trying to integrate it, go find what the inner function is. It's always going to have some sort of inner-outer situation. If you can find what the inner function is, it is usually that you want to call u. If it ends up being not that you wanted to call u, like sometimes it can be a little tricky figuring out, what should I be replacing with u? You could always try it and see if it works. If it doesn't help you, go back to square one and try something else. But for the most part, if you think about it as the inner function, you're going to get it right. So let's say u equals x cubed plus 2. This means I can rewrite the integration that I'm trying to evaluate as the antiderivative, or the integral of u to the 10th power. You can see how I replaced the entire parentheses with the letter u. But it is still times 3x squared dx. And again, I have this mismatch of variables. I cannot do the antiderivative until I get all of the variables to be the same. They got to all be in terms of u. So I'm going to go back to where I defined u. The practice is find du dx, which is another way of saying the derivative of u. Derivative of x to the third plus 2 is going to be 3x squared. The plus 2 just has a derivative of 0, so it goes away. Remember, these are derivatives here, not antiderivatives. Pass the dx over to the other side so that we don't have it as a fraction. And indeed, what you see, like I said, they chose numbers really nicely for you. This 3x squared dx is exactly what I have over here in this integration. And so I can, by substitution, swap it out with this du. So the antiderivative of u to the 10th du is what I'm trying to integrate. It's now all in terms of u. I'm ready to do the antiderivative. U to the 10th is just a power rule, so I have an antiderivative rule in my formula booklet for u to the 10th, and that is to increase the power by 1 and put it over the new power. Don't forget the plus c. And then in the end, you got to change u back to whatever you defined u to be, and plus c. And of course, it is good practice to do the chain rule and check if you got it right. In the interest of time on the video, I will skip that step, but you may want to pause and practice your chain rule check to make sure that you got the antiderivative right. Let's skip ahead to, how about e, where we've got an e function. That's pretty funny. Again, first step, you want to scan this, look for what you kind of would consider the inner function. Here, that's going to be this 3x plus 1. And we're going to define u to be, just dismiss that. We're going to define u to be 3x plus 1. We're going to want to take the du dx of that. You always need to do this step, so you might as well just get in the habit of doing it, and then pass the dx to the other side so we could see what du is equal to. And now I'm going to, and I've color-coded this on purpose, all the work I'm doing with u and du dx I've done in red, and all the integrations I've been writing in blue. So I'm going to go back to the integral. I'm going to change it to e to the u power. But I still have that dx there. And now I got to figure out how am I going to do a substitution to make this thing work out. It's dx that I need to replace, but up here it's 3dx that I have in my equation. So since it's only dx that I have in the antiderivative to replace, or in this integral to replace, I want to make sure I have only dx by itself. So I'm actually going to pass this 3 over to the other side with the du. And rather than doing it by division, it's going to be extremely helpful if you always think about it as multiplication when you're trying to move things around this equation. So the 1/3 will cancel out the 3, and on the left side we end up with 1/3 du equals dx. So that now, when I come back to the integral, e to the u, in place of dx, I can put 1/3 du. So 1/3 du. This is all multiplication in this. 1/3 just looked crazy. This is all multiplication in this integral, right? It always is. We just don't usually show the dots for the multiplication signs. And so that 1/3, the positioning of it, it doesn't really matter. I could actually rewrite that just for the visuals of it as 1/3 e to the u du. So if you notice that that 1/3 is just a coefficient, then you're actually ready to do this antiderivative, because a coefficient in an antiderivative just stays there. E to the u's derivative is e to the u. Put a plus c. Notice I've dropped the integration symbol because at this step I actually did integrate it. It just happens to look exactly the same. Now I've got 1/3 e, got to change the u back to 3x plus 1. And don't forget the plus c. And this is the original function that had as its derivative e to the 3x plus 1. You could always check it by doing the chain rule and making sure that the derivative comes out to what you want it to. Let's see what we've got on the next slide for further practice. Does it get harder? Oh, sure it does. Probably B is the hardest one here. So maybe we should do B on this video. And we will continue to practice when we're together in class. But just so you've seen a few examples done out. What's tricky about B here is figuring out what to call U. And I've advised you to look for an inner function. But I'm going to write this out a little bit bigger. When you see sine squared x, cosine x, dx, it doesn't really look like there is an inner function. It looks almost like a product. But I am going to task you with looking for that inner function. So if you're looking for it, maybe you will see it, which is that this sine squared x, we must be in the habit of seeing that as quantity sine x squared. And you could always rewrite it with parentheses so that you can identify that you actually do have an inner function, outer function situation. You have sine x on the inside and a squared on the outside. So this is an indication to us that we want to let u equal sine x. I like to go over to the side, define what I want u to be. Take the du dx. What is the derivative of sine x? It's cosine x. And then pass the dx to the other side, because you'll always want it on not the same side as the du. And then check out what you have in your function. So you actually do have a cosine x dx, which is exactly what we've got as equal to du over here. So all my substitutions are going to work perfectly. I'm going to integrate u squared du. What did I do there? I replaced sine x with u, because that's what I defined it to be. And I replaced cosine x dx with du, because that's what it came out to. I have a function I can now do the antiderivative of using my formula for power. Increase the power by 1, put it over the new power, do a plus c, and then change it back to sine x. Notice it was to the 3rd power, so I'm going to put the cubed in there. That's typically where we show it in a trig function. And then, of course, you could check your answer using the chain rule if you had time. So that should be sufficient for you to see the types of problems we're going to need chain rule or a u-substitution for, and some of the nuances. So you'll have to just practice make perfect, and we'll practice more of these together in class. That is all.